something that's essentially like hot space.
Yeah, and then certainly one that I'd always wished we had done, but there really were implementation difficulties, was true virtual block addressing. Because it would have made dedupe simpler, it would have made compaction of data, defragging, all that kind of stuff simpler. That would have been really nice to have. But we never did come up with a way that was sort of tractable in terms of both the cost and the transactional semantics.
Yeah. I mean, maybe if we had insisted on like, oh, you have to have a hybrid pool with SSDs and metadata and disks in a fixed ratio and whatnot. But I think that if we had done that, it probably would have had a big impact on the, how widespread use of ZFS is, because like the flexibility of it and the ability to work with like without requiring that kind of hardware is part of its success.
Yeah, one that's sort of less obvious, because it's not like an explicit design choice. But in order to make Z-test work on our workstations, right, we had to have the files and /temp for our little simulated virtual devices. They had to be kind of modest in size, and they were like, I think 64 meg or something, because we didn't want to run out of memory. And as a result of that, in order to be able to run Z-test under some like worst case workloads, it forced us to be very precise in our accounting of every time you wanted to do a transaction, exactly how much space was going to consume, because if we were off by even a little bit, we'd run out of space in the VDEVs, and then the test would fail kind of artificially. And I really, really wish we had just said, our files in /temp are like at least a gig or 10 gig or something that was much closer to the size of a disk drive, because then we could have just said, if you ever looked at like DMU-TX assign or DMU-TX, like whatever it is, estimate space,
size, yeah.
It's horrific. Yes. It's so bad.
I wrote all that code. I wrote all that.
It's not your fault.
That code is horrible. It is absolutely horrible. And I like all the things that you just said, I've spent lots of time dealing with, because we have, like, for example, when we increased the maximum data block size to from 128K to 16 megs, we ran into a lot of these issues. And then right now I'm working on increasing the metadata block size default from 16K to 128K. And that hit even more crazy things in that accounting code, which it's like, yeah, the code is wrong, but man, it is so tricky and it matters essentially never. Mm-hmm. We should have just explicitly defined it to be like, it does not matter.
Yeah, and the way to do that, which would have been really, really simple, is you just say the minimum pool size is some large-ish number, like tens of gigabytes, and the implication would then be that any I/O that you ever accept, because the MTU is like whatever, a block at a time or some number of blocks at a time, any I/O that you let in the door, you have enough space to finish, right? And you could be very coarse about it. And it's actually at my startup, the SSD, that was one of the things that we did is, we're like not trafficking in less than terabytes worth of space, and so all the space accounting code, there just isn't any. It's so nice.
That's so nice. Other questions? Yes.
So one of the things that I've always kind of wondered, so now we've all given up on the idea of like spinning Rust, right? Like we'll only use SSDs and that's the way it works.
Have we? Is anyone in here using spinning Rust?
Wow.
Oh.
So in a world where those people didn't exist, is there anything you would sort of approach this problem that you were trying to solve differently, where you didn't have to worry about that? Like you knew it was only going to be, like solid state.
Like for example, a startup you sold to EMC for $1 billion.
Yeah. So what we did there, that was a very different design. We were trying to design a product just to go as fast as humanly possible, and it wasn't about the feature set. It was just about absolute best possible block device performance. But I wouldn't want to use it for my daily life, because I actually want all the features that come with ZFS. It's really nice for work as a developer. And actually a lot of ZFS was about scratching our own itches that we had developed over the years. Probably the biggest thing is that one of the things that was a fundamental assumption going into the design of ZFS is we had looked at the trends in Moore's law over the course of the previous decade, going from like 1990 to 2000. And what you saw is that storage devices had gotten about 10 times faster, memory about 100 times faster, CPU about 1,000 times faster.
And the storage was 10 times faster throughput.
Right, and the IAPS never got better. Right. So you look at that and you say, well, back in 1990, everybody was really worried about the cost of a B copy relative to their file system. And by the time the year 2000 rolled around, it really wasn't that important. If you had to copy the data, or if you wanted to run a checksum on it, compress it, dedupe it, you know, you got multiple cores, they're running at multi-gigahertz speeds. It's an entirely reasonable thing to do when a disk is still, you know, a several millisecond operation. Well, with flash, the time to read flash is now, depending on the vendor, you know, on the order of like 50 to 100 microseconds. That's a lot faster, right? And when you change performance by that large of a multiplier, it does kind of call some of your assumptions into question. In particular, like the box that we did at DSSD, the total CPU budget that we have for an I/O is about 3 microseconds for the code and any cache misses that happen, right? And you can't actually do all the stuff ZFS does in 3 microseconds. It's not possible. Yeah. So I'm not sure what I would do about it, though.
Well, I think
because I want a box that goes as fast as Flash, but has all the features of ZFS, and I think we just need special hardware for that.
Well, I think it just makes our job a lot harder, right? Like, I mean, I wouldn't have necessarily changed any major design stuff about ZFS because, like, you need checksum and like you need compression, maybe even more so on SSDs because they're so much more expensive per gigabyte. But I think that we would have put much more thought up front into, you know, streamlining that code path so that it's like we do the compression, we do the checksum, and then like you have 2 more microseconds to do all of the rest of the stuff, like all the locking, all the space accounting. And that's certainly something that we can still invest in doing. And I know, you know, several of the vendors here have talked about that.
Jeff, what about virtual addressing, something you had mentioned earlier? If you get, you know, reads or 50 mics or 150 mics, would that make virtual addressing possible?
Yeah, it definitely would. The challenge, of course, in the ZFS community is that unlike being an appliance vendor where you're optimizing for a particular box, here we're trying to optimize for everything, right? So you want to be able to work on a laptop and also on some very high-end config where you've got a mix of, you know, spinning Rust and Flash and, you know, future non-volatile memory technologies. You know, the previous talk is a perfect example of if you could take metadata and put it somewhere else so that that stuff goes really fast, so like a find, you know, it's just like that. That's really compelling. But at the same time, you don't want to depend on it. The problem with virtual addressing is that it's sort of not optional as a feature. You either do it or you don't. And so you, at that point, you're basically assuming the existence of very fast metadata reads. Yes?
Speaking of making your job harder with virtual addressing, what's your opinion on ZFS supporting native clustering?
My opinion is that clustering is really like making an actual clustered, you know, all nodes writing at the same time file system is really, really hard. Like on the same order of magnitude as implementing all of ZFS that we've done so far. So like, you know, engineered decades. I do have a back of the napkin design for like a sort of semi-pseudo clustered ZFS, which I'm sure you've probably heard this story many times in the past, which I won't get into today, but essentially, you know, if you divide the space into chunks and assign each chunk to a computer and assign each file system to a computer, then it simplifies the problem dramatically. It also means that, you know, if you only have one file system, then it doesn't solve this wouldn't solve your problem. So I think it depends a lot on the use case. You could do something like that. It just depends. Even that would be, you know, you'd be talking about lots and lots of engineer years to implement. But the design doesn't exclude it if you are willing to draw the boundaries around the solution kind of in a particular way. Did I see it? Yeah.
Have actually ever lost your personal data from ZFS book crash?
Have either of us lost personal data? No.
No?
Yeah. I think if anyone in here has lost data due to a bug in ZFS, like, I may have to buy you a beer or something. I'm sorry. That was definitely like, I mean, from day one, we knew that data integrity is key. And if you look at some other file systems that have not been as successful, I think one of the reasons is because once you use it and you discover, oh, this thing has tons of bugs and it just crashes and loses my data, then it's probably like 10 years before you go back to look at it again.
Yep.
Yeah.
So going back to a question Adam asked about features that maybe you whiteboarded, can you talk about the grid bits and the block pointer?
The grid bits and the block pointer. So I don't even remember what those were originally going to be. We had some like cockamamie scheme in mind that we never ended up implementing. Right before I left Oracle, the last project I did that unfortunately was in build 29, not 28, which is the one that was the last one that was open sourced, was a support for RAID Z and mirror hybrid. And I think the way I ended up using those bits was the thing you need to know for any given piece of data. So just real briefly, the idea for that is to say, if you're storing most of your data in RAID Z, or let's say you're storing all your data in RAID Z, and you have a relatively small amount of metadata, the thing that's annoying about metadata is you want it to be very fast to access, but in RAID Z, if you're reading it like a 16K block that compressed down to 1.5K, that's 3 separate sectors back when it was 512 everywhere. And that means in RAID Z, you've got to do those 3 separate reads just to get your one piece of data. So the idea of RAID Z mirroring, sort of hybrid, was to say that what you do is you still use the RAID Z layout for everything, but when you're storing metadata, instead of, let's say it's 5 drives, instead of it being a 5-wide RAID Z1 or RAID Z2 stripe, you actually just make it a 5-way mirror of that particular piece of data. And I sort of debated between making it a 5-way mirror or like taking it and cutting it up into like 2 pieces, and then you have to do like 2 IOs instead of. But basically, if you're trying to make it go faster, you may as well just eat it, because the metadata is on the order of like 1%. And so even if you're making it a 5-way mirror, okay, so now I just multiplied it to 5%. Still reasonable if you get a decent performance boost out of it. So what ended up going in those grid bits, I believe, was a 0 if the data was mirrored, and otherwise it was like 1, 2, 3 if it was RAID Z1, RAID Z2, RAID Z3. I think that's what I ended up putting in there.
I believe it.
Yeah.
I find it interesting that you brought up if you watch the old videos of ZFS, you say the same thing about how you wanted the box to be the same as RAM. You wanted storage to be RAM. I find it interesting that you brought it up again, because I feel like that was, because I go through a talk where I give people kind of what ZFS did really great, and some of the things where I didn't think they did great, but you brought it up again. Do you guys think that the system you built does make storage more like RAM? Because then it sounds like the block pointer rewrite would have been really high up on their list of things to either complete or make easy to complete, because you'd say, we want to just tip the box over, throw in more disks, and have this thing perform in a way that you expect.
I don't know. I guess I would give us partial credit. I think that in an ideal world, you would be able to just specify which disks are to be part of the pool and what quality of service you want for each kind of data that you're storing, and then everything just gets dynamically handled. In practice, that just turns out to be really hard. Not so much from a coding perspective as much as setting people's administrative expectations and being able to understand, when I remove this device, how long do I have to replace it, and what are the boundaries of my failure domains. And in that sense, storage does have a little bit more of a personality than DRAM does, because every DIMM in a computer is exactly the same. There's no personality difference. Not so for disk drives, unfortunately. Especially when you've got a combination of, low and high RPM drives, different capacity drives, spinning Rust versus flash, and the flash in turn between SLC, MLC, and TLC, and then a whole bunch of next-gen stuff. You've seen like Intel's 3D Crosspoint, and there's other things out there as well that are coming in the next year or two. So we've gone from, in a very short amount of time, really, sort of in historical perspective, we've gone from multiple decades of disk being the only storage medium for primary storage, really, to now all of a sudden they're just coming fast and furious, and it's going to be hard to adapt to that because storage software, as far as I can tell, can't be developed in less than 5 years.
Speaking of next-gen technologies, I'll ask you a question, Jeff. Which technology is going to be first to non-volatile main memory, and how many microseconds until it's delivered?
If I had to make a bet,
Do you want to admit to why I'm asking this?
yes, but I'll give you my guess first. If I had, well, it depends. I'm going to say there's a little company called Nentero that's doing some very interesting stuff, very, very low latency, really good properties in terms of its endurance. So I'll put my bet there.
Right.
And you're asking because?
Well, I'm asking because you've stated several times in the past when this would occur.
Yeah, and I just stopped betting.
Okay.
Because it's kind of like, there are certain things that people keep predicting. All right, it's still going.
Resiliency.
Yeah, exactly. There's certain things people just keep predicting that never actually happen, and it seems like non-volatile main memory is one of them. So I'm not going to hold my breath.
What comes first, non-volatile main memory or nuclear fusion as a reactor?
Yeah.
I have no idea. I'm not a nuclear physicist.
I'm actually going to say non-volatile main memory. There's at least like prototypes of that, as opposed to fusion where. Yeah.
So, well, 15 years ago, did you guys actually think that ZFS would be as popular as it is now?
Personally, I hoped it would be this popular. I'm still pleasantly surprised that it actually is.
I mean, even when I started working on ZFS 14 years ago, I was like 21 years old, straight out of college. So yeah, I had no fucking clue that it was going to be this popular.
Yeah.
It's pretty cool.
I think 10 years ago, when we first released it,
Yeah.
we didn't have any idea that popular it would be what it was, from the community.
Yeah.
Yeah, I agree. Even 10 years ago, I think we had no idea.
Yeah, and then the other thing that you wonder, even the day you release it, is all right. 2005 Halloween, here it is. In 10 years, will it still be relevant? Mm-hmm. And that's the other thing that's been a real pleasant surprise. Not only is it still relevant, it's still growing, accelerating, and I would say still best of breed.
Oh, yeah, I agree. I think, if you'll let us indulge in patting ourselves on the back for a moment, I think, one of the reasons for that is because, the original design that we did was relatively clean. We separated out the concerns like decently, and that's allowed a lot of extensions on top of ZFS over the years. Like dedupe, for example, was only implemented, 10 years after the original design? We started in 2001, and it was, right. Dedupe was shipped in, maybe not 10 years, but 7 years?
Actually,
something
Dedupe
like that?
Was like 08 or 09.
Yeah, so 8 or 9 years later, really major feature added to ZFS with relatively little
testing.
Relatively little having to rework the existing design, right? kind of fit in. And I think a lot of the ideas that we've seen today, even the more far-fetched ones, you can kind of see how it would fit into the existing framework of ZFS. Other questions? Yeah, Joe.
Why Halloween? I think the first time it was entirely coincidental, and then we kind of just said, and if it had been like October 27th, we probably would have forgotten about it. But it was sort of memorable that we were doing it on Halloween when we sent out our very first like hello world from the user level prototype. And then, as it came to be about like summertime, and we're working on the kernel code, we really wanted to get October 31st again in 2002 for first kernel mount. We actually did manage to pull that off. God, and it was like, we were so, in a way, it was like so close to done, right? It's like a year in and you've got to first kernel mount. And it was so far from done. I mean, really like 90% done, 90% to go. It was so true. It was like 90%, first kernel mount, you are 90% there. And yet, it really did take 10 years to get to a point where you could say with a straight face, deploy this in an enterprise environment.
I agree.
Was there a point along the way where you were like, maybe we needed like burn everything to the ground and start over from scratch?
I would say yes, multiple times, but it didn't mean like burn the whole thing to the ground. There were multiple rewrites of major subsystems. So, there was a SPA 2.0, a SPA 3.0, a DMU 2.0, ARC 2.3. We've been through major revisions on every major subsystem.
Even the command line set.
Right, even the CLI.
Command line set was kind of horrific.
It was actually pretty bad, yeah. And I'm largely responsible for that. I had this like idea that everything should be, like all the ZFS subcommands should be named after like things that you were used to in user bin. So it was like, ZFS LS and ZFS, I don't even remember what all the different things were.
Yeah, I don't remember
But
either.
they were,
The first VDEV specifications where you actually had to
Oh, parentheses?
yeah, you had to put all
oh,
Yeah.
yes, they were mathematically beautiful, but horrific to type. And basically the problem was that it would have been fun. So basically, like, when you specify VDEV now, right, you say like, RAID Z and then list of devices, right? And the original idea was that you could have, your VDEVs could be layered. So you could have like a mirror of RAID Z, and you could have, mirror of RAID Z of mirror of, there's no limit in the actual code. And so to express that on the CLI, I expressed it the way you would as any mathematician would. It's like, RAID Z, open paren, mirror, open paren, blah, blah, blah. And of course, if parens were not special to the shell, that would have been fine. But they are, and it was just awful. So you had this single quote. We really can't go into an editor war right now.
Any questions that will not spark a war? Yes.
So who was responsible for the better command line design that we all
Eric Schrock.
VP of Engineering at Delphix. Shout out.
Mm-hmm. That was actually the first thing he did at Team ZFS.
Yeah, I think so.
Is he basically came in, and this is great. He's just like this kid fresh out of college, and he's like, "Your command line sucks." I'm like, "Excuse me?" He's like, "No, really, it sucks." And I'm like, "You want to do it?" He's like, "Yeah."
Okay.
All right.
Jeff, it was all driven by DL-Sim at the time.
Oh yeah, it was. It was more dynamic than it is now.
Mm-hmm.
And more terrifying.
Yeah.
How much of the design was driven by iteration and failing it, rewriting it, versus getting it right on the whiteboard the first time?
Well, I think it depends on what, like design of the CLI or kind of everything.
Talking in general, like the file system layout, the allocation code, whatever.
I mean, I think that we got the big picture like pretty good from the beginning. The implementation, like as Jeff said, lots of rewrites. But I think that most of those were rewriting the implementation because we're only okay coders.
Yeah. Basically, like if you look at the sort of big block diagram of how ZFS works, that was essentially the model that we had in mind from within the first couple months of thinking about it. But things like how exactly snapshots are going to work, the fact that there's dead lists as opposed to some other data structure, the distinction between a data set and an object set, which I still can't keep straight. We didn't have all that stuff worked out. There were a lot of little nuances, and that and the whole like SPA sync to convergence algorithm, that turned out to be tricky.
But most of that was worked out certainly within the first year, right?
Mostly, yeah. Yes.
Not
It wasn't.
just
No,
UFS.
it wasn't actually UFS as much as it was Metadisk, the underlying volume manager. I mean, UFS we had issues too, but those actually had more to do with hitting limits of scale, right? Because we were trying to get to, UFS was designed in a much earlier time, and we had even things like just on-disk structure constraints, right? Like the inode is only so big, and certain fields are only so big, and if you're going to change something incompatibly, then I think we knew very early on that we wanted to be, well, I know we knew very early on that we wanted to be transactional, simply because the idea of running FSCK on ever larger data sets becomes implausible, right? It's not physically possible. You can't do that. And there had been, fortunately, a lot of work not only in the database community, but in the file system community on how to achieve that. The other one that I knew was going to be important was data integrity, and it just struck me as bizarre that there was no file system out there that actually checksummed its own data. That just seemed weird. Because we knew from experience that getting the wrong data back from a disk drive or an array, that's a thing that happens. And if it's metadata, the system just goes berserk. Any others?
I'll take another question.
Sort of a follow-up on that. I've always been curious how much you guys, or if you did at all, study sort of database technology at the time. Because when I look at this implementation, I see database implementation all over it. But I've studied that quite a bit. But maybe you guys never have, or maybe you did look at it a lot.
Yeah. I'll give you kind of two small data points. One is a very direct pull from databases, which is the ZAP, which is like the Ondisk mapping from name to values, used for directories as well as other stuff. I got the idea of how to implement that from literally from a book about databases. It's implemented using extensible hashing, which is used a lot in database indices. Also, I think during the time, wasn't Microsoft working on the file system whose name I forget that was supposed to be they had no metadata. It literally ran a database in the kernel. WinFS, yes, WinFS. But I don't remember any details from that.
Yeah, no, I think for, well, in some ways, everything in computer science is the same. There's 43 architecture diagrams that, you pick one and it pretty much describes your product, right? And for me, it was more of the analogy with the VM system was the thing that I saw as kind of driving us. And so, hence the term, we use the term in all of our early presentations. We talk about copy on write, as opposed to a database person would talk about shadow paging, right? It's the same thing. But if you come from a VM perspective, you think more of cow, because when a process forks, right, you have two mappings to the same page until somebody touches it, and then it splits into two.
So how did you come up with the design for LZJB, which I assume stands for Lempo Ziv Jet?
Yes. Okay. So LZJB, that's the one sort of, obnoxiously ego thing, right? To have my initials on it. But it was just because that's sort of the way it's done in the LZ world, right? So Lempel and Ziv had the actual idea in 1977 for how to do dictionary-based compression on a stream of data. And there have been tons and tons of variants, all basically named by the initial of whoever was involved in it. So the goal for LZJB was that all the other LZ derivatives that were out there were a lot of code, and I didn't feel like I could, and they relied on certain things about their environment. A lot of them required memory allocation. And I wanted something that didn't require memory allocation because it was going to be in the I.O. path. And I wanted something that was small enough that you could look at it and inspect it and be sure that, yeah, this is actually correct. And it turns out if you go back, if you look at implementations out there of various LZ compressors, a lot of them are really, really complicated. If you go back to the original paper, what the actual algorithm is, it's really simple. And the actual LZJB code it's like 60 lines or something. I mean, it's really tiny. It's you know.
When did you implement it?
That was actually one of the first things that we did. We had compression, I think, from pretty early on. It was like 02 or 03, maybe.
You didn't. I thought that you'd implemented LZJB for crash dumps.
Oh, right. You're right.
So
LZJB, you're right. That actually, you're right. The original motivation, you're right, wasn't
all this
ZFS.
is true, but it wasn't because of ZFS.
But right, but it wasn't because of ZFS. It was because for generating crash dumps for Solaris, we had noticed the data was highly compressible, and it took forever to write crash dumps out, especially as memory got bigger and bigger. So we decided, well, it'd be cool to compress it on the fly, but when you're generating a crash dump, the operating system is in a very compromised state. So you can't be like invoking the memory allocator or invoking any kind of services at all. It's all got to be code that has essentially no context, right? You just show up with your buffer, you do some compute on it, you're done. And so it had to be very, very minimal for that.
Maybe if
And then we just dropped it into ZFS.
Yeah. Maybe if we had implemented it specifically for ZFS, we would have thought of calling it like LZZ or something silly like that.
Yeah.
How much you experience on doing the film slab allocator helping ZFS?
So how much did the slab allocator help in ZFS? Well, I guess there's actually a little piece of history there. So you know how our main chunks of storage are called meta slabs. That's because in the beginning, the idea was that just like in the slab allocator, where each slab is cut up into chunks of equal size, in the very beginning of ZFS, we had the same idea. That we were going to say, we partition the storage into meta slabs. Each meta slab then consists of all 4K buffers or all 128K buffers or whatever. We found very quickly, of course, that just leads to horrific fragmentation that you can never recover from, right? If you allocate nothing but 4K stuff and then free it all, or all but like one block from each meta slab, now you're hosed. You can't ever allocate any other size. So the name ended up sticking, but the algorithm changed, and of course now has nothing to do with slab allocator at all. It's really just like a pretty classic first fit. It gave me confidence. Baseless.
No. Other questions? Anybody in the back? I don't know if I haven't seen your hands. Stick it up again, please. No? Okay. Maybe everyone wants to go to dinner.
Yeah.
Great. Thank you. And we'll cut the cake later. Yeah.